Welcome back to our discussion in 9.5 now, where we're going to introduce alternating series. And so we're continuing our quest in dealing with different types of series and understanding how can we determine whether or not they converge or diverge, specifically if they're not one of these special types of series, telescoping, geometric, and now also p-series. And so one instance or a type of series that we can run into is what we call an alternating series. A very specific type of series. It has a very specific type of term in front, which we introduced in 9.1 in sequences, which is a -1 to an n or -1 to the n plus 1. What this is going to do to my sequence is it's going to change the signs, right? It's going to flip signs positive, negative, or negative, positive for all of my terms. It's not going to affect the values of a sub n, just the signs of a sub n. Why do I care about that with series is because now remember when we go to add things up, we are now adding negative numbers. In fact, half of the terms are now negative. And so a lot of those plus signs become minus signs. And so for example, in this case, we're going to end up with minus a1 plus a2 minus a3 plus a4 minus a5, where now half the terms have been subtracted and half the terms have been added. Same thing here, the only difference is we're starting with a positive a1 minus a2 plus a3 minus a4 plus a5, And so we're given an alternating series. It is assumed that a sub n is positive, so I'll write that or add that. A sub n is positive, so we don't have to worry about doubling down on negatives if a sub n was also negative. That way we know that we're alternating the entire time. And what is the benefit of alternating? Actually, when it comes to convergence of series, it now makes it a little bit easier for a series to converge. If you think about it, right, where it used to be all addition, adding, and hoping you get something finite, now it's like you take a step up, you take a step back, you take a step up, you take a step back. Addition, subtraction. So now it's a little bit easier to actually control that infinite sum. And things that might have used to diverge now could possibly converge. And we're actually going to see that happen. And so alternating series looks like this. Alternating series also can be disguised, so we don't want to be fooled by trig functions. For example, cosine of n pi, that's going to end up being -1 to the n. If you think about cosine, right? Cosine oscillates between 1 and -1. And if you actually just look at the multiples of pi, so cosine of pi, cosine of 2 pi, cosine of 3 pi, cosine of 4 pi, that's actually -1, 1, -1, 1, -1, 1. And so it's nothing more than this. Same thing, right? We can also do the same thing with sine. It's a little more complicated with sine because sine is 1 and -1 at multiples of pi over 2, odd multiples of pi over 2. And so it's going to be sine of pi over 2, sine of 3 pi over 2, sine of 5 pi over 2, sine of 7 pi over 2. Those are going to alternate between 1 and -1 and can be encoded like this. But again, that's nothing more than this alternating series. And so sometimes they can be disguised, so we don't want to be fooled. If we see something like this in front, see it for what it is. It's nothing more than this -1 to a power. And so, like I said, the alternating series are a little bit easier to control those infinite sums. In fact, so easy that the alternating series test is probably the easiest test to run. It says that given an alternating series, I use -1 to the n, but it could have been this either way, for simplicity's sake. If the sequence that's being alternated, so a sub n, so without that -1 to the n, right, that's just what's making it alternate. The thing that you're alternating is an. That's the sequence that has signs being changed every other term. So if that sequence, a sub n, is going to 0 and getting smaller, that is actually sufficient. That is enough to then say that the series converges. If it meets these conditions, then the series converges. Those are very simple conditions to check. In fact, that would be like an ideal case, even back at the beginning. If all we had to do is make sure we were getting smaller and going to 0, then we wouldn't have all of these other tests. And fortunately, for an alternating series, that is enough. If your series is alternating, all you need to know is that the sequence that is being alternated is going to 0 and getting smaller. Then it will converge. While this test is very easy, it has no conditions for divergence. You notice all of our other tests, if it's a special series, you have both conditions, convergence and divergence. Integral test, right? If the integral converges, the series does. If the integral diverges, the series does. Comparison, right? You're comparing it to something that converges or diverges. And so all of our tests so far have been both conditions, right? We have a conditions for convergence and a condition for divergence. This test is only a condition for convergence. It does not say anything about divergence. We don't want to make the logical fallacy of assuming that if we do not meet these conditions, you diverge. That is not true. Think about a very simple statement. You have homework due, say, on Mondays. And so if it is Monday, then you have homework due. Now, that is a true statement. That does not mean, though, that if it's not Monday, that you don't have homework. Because you might have other classes, and you might have homework due on other days for other classes. And so if it's Monday, you definitely have homework due. But if it's not Monday, it doesn't mean you don't have homework. And so we don't want to assume that if it doesn't meet these conditions, it doesn't converge. That is not necessarily true. All we know is that if it meets these conditions, it converges. Now, the proof of this statement, why is these two conditions the only things you need for convergence, is very elegant proof. And in a different video, not in this one, I will present that proof to you. But for right now, let's just assume this is true. No condition for divergence, but if we meet these conditions, we converge. And so that means now let's look at some examples. Say we're given an alternating series. Something like this. -1 to the n times 1 over n. And so the sequence that's being alternated, my a sub n, is 1 over n. What do I know about 1 over n? Well, I know its limit is 0. Is 1 over n decreasing. There's different ways of going about that, right? We talked about monotonicity back at the beginning of chapter 9. And so is 1 over n plus 1 less than 1 over n? Right, the next term in the sequence is smaller than the one before it. Remember, decreasing, we can encode it like this, monotonic. Is this true? Yes. Yes. So this series converges. This alternating series converges. If it didn't meet these conditions, I would not have an answer necessarily, and so we always have to be mindful of that, but in this case, this series converges. So if we meet these conditions, we converge. Now, although this might not look alternating, remember cosine of n pi, that's just a fancy way of saying -1 to the n, and so we can really think of this as -1 to the n over n squared. And so the thing that's being alternated here is 1 over n squared. What do I know about 1 over n squared? Its limit definitely is 0. If I look at the next term, n plus 1 squared, is that going to be less than 1 over n squared? Yes. Bigger denominator, smaller fraction. Yes, check, check. It meets both conditions. This series converges. And you see how fast it is to determine the convergence of an alternating series if it meets these conditions. Just two very simple things to check, getting smaller and going to 0. And so these are nice conditions. Now, of course, this brings up an interesting scenario because, well, we talked about alternating series. It makes it a little bit easier for something to converge. In fact, if you look at 1 over n by itself, if I considered the non-alternating series just 1 over n, if I got rid of that alternating piece and just considered this, we know that this series diverges. So even though my alternating series converges, without that alternating piece, it would have diverged. In this case, if you look at this series without the alternating piece, 1 over n squared, that actually converges. And so without the alternating piece, it would have made a difference. It would have converged anyway, but this one, it did make a difference. It wouldn't have converged without the alternating piece, without that -1 to the n. And so this is going to bring up a special definition when we talk about alternating series, and that's going to be what we call, is it conditional convergence or absolute convergence? For example, here, this alternating series converges, and we're actually going to add the word it converges conditionally. Conditional on the fact that it was alternating. And I mean that without that alternating piece, it would have diverged. So what's saving it, or what's making it converge, is the alternating thing itself. It converges because of the alternating thing. So it's conditional on it. It's conditioned based on the alternating piece. Here we would say, oh, it converges, and even if I got rid of that alternating thing, it wouldn't have made a difference. It still would have converged anyway. We're going to add the word absolutely. It converges absolutely. And absolutely doesn't mean we're really excited about it. Absolutely actually means something about the absolute value, right? Making everything positive, i.e. getting rid of that alternating thing. And so let's write out those definitions. So given an alternating series, and so say we're told that that alternating series converges, right? Like in the last two examples, we found that both those series converge. Then we want to ask ourselves the additional question. The additional question is, what happens if I get rid of the alternating piece? If I get rid of the alternating piece here, and say it diverges, then we would say, okay, well, this series still converges, but converges conditionally. And if I got rid of that alternating piece and say it still converges, then we would say, okay, well, this series converges absolutely. And again, the word absolutely comes from the fact of the absolute value, making everything positive. How do you make everything positive? How do you get rid of the alternating piece mathematically? Take the absolute value of everything. That's going to make those minus back into plus signs. As an example, let's say, we have this series. What would I say about it? Well, it's alternating. What is being alternated? 1 over n plus 2. Well, what do I know about 1 over n plus 2? Let's see. The limit is 0, so that's good. Is it getting smaller? So if I look at the next term, is it smaller than this term? Yes, right, because I made a larger denominator, so a smaller fraction, so check. And we would then say this series converges. So I know that this series converges. Now the question is whether or not it's conditional or absolute convergence. And that now goes into, let's get rid of the alternating piece. Let's ask ourselves another question now. What happens if we only consider this? Well, in this case, I would say it's similar to a p-series. And using limit comparison, we would say that this series then diverges, right? What do we know about 1 over n? This series diverges. I think it's similar to that. That's my claim, right? We talked about that in the last video. Using limit comparison, I won't run it, but you could run it and it would give you the answer. Using limit comparison, we know that this series diverges. And so what does that mean? That means, okay, my series converged, my alternating series converged. Without that alternating piece, though, it would have diverged, and so we'll say this converges conditionally. If I do this, and for some reason I get that this series also converges, then I would say this converges absolutely, right? So these are the extra words that we're going to add in. And so alternating series have to look a very certain way. It's very easy to check those conditions. And then we only need to add some extra words, right? The idea is if I get rid of the alternating piece and it still converges, we say absolute. And if I get rid of the alternating piece and it diverges, we would say conditional. And then the only other thing would be, what if it's not quite alternating? It's alternating, but not quite alternating. Maybe something like this. Sine of n over n squared. We'll write out the terms, right? This is sine of 1 over n1 squared plus sine of 2 over 2 squared plus sine of 3 over 3 squared plus sine of 4 over 4 squared, sine, I'll do one more, 5 over 5 squared. We get the point, dot, 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 dot. And you know that sign alternates between 1 and -1, but if we look at sine of 1, sine of 2, and sine of 3, these are all positive. So they're plus terms. Right? Squaring the denominator always makes you positive. So the first three terms are going to be plus, plus, plus. Oh, but once I pass pi, or 3.14, these terms are now negative up until I hit 2 pi, or 6.28. And then once I pass 6.28 about, I'm going to get positive again. So it's not alternating. Right? It's like plus, 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 minus, 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 plus, plus, minus, 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 minus. And it's not going to alternate as it should in definition, right? So it's not alternating. The first thing to note, it's not alternating. So I can't use the alternating series test. Well, the only other tests I have require positive sequences. And so let's consider the absolute value of my series. Let's make everything positive. Now, absolute value in the denominator doesn't make a difference. But now everything's positive. Everything is now positive. Why do I care to make everything positive? Let's think about why talking about the positive version of everything would help me answer the not alternating, but the including negative term situation. And that goes into a very simple, well, we'll call it a theorem, but it's a statement, is that if the absolute value of a series converges, then the series itself converges. Think about just the basic understanding of this theorem. I'm not going to prove it, but it's very simple and intuitively. If you make everything positive and your sum is finite, then by reintroducing negative terms, you're only going to make the sum smaller. You're not going to make it any bigger. So if the sum, as everything being positive, is finite, then the sum with negative terms added in is not going to be any larger, and so therefore will also be finite. And so if the absolute value converges, then this series itself does. And that is what I'm going to try to do here. I don't know about this one. It's not alternating, so I can't use the alternating series test. But let's consider the absolute value. Now that everything's positive, I'm going to use direct comparison. Direct comparison to what? Well, 1 over n squared. Why 1 over n squared? Because sine is periodic. Sine always goes between 1 and -1. So the absolute value of sine always goes between 0 and 1. And so the most that sine could ever be is 1. Meaning regardless of what n is, the most the numerator could ever be is 1. And so this will always be less than or equal to 1 over n squared, regardless of what n is. That's the most it could be. And why do I care about that? Because now I am smaller than something that converges as a series. We know that this is a convergent p-series. I am smaller than something that converges, and therefore this series also converges. So wait a minute. If I make all the terms positive, it converges. Well, certainly then, if I get rid of the absolute value sign and now I make some of those terms negative again, instead of taking absolute values of everything, then it would still converge as well. And so now we can say with confidence that this series also converges. And that's just a little add-on to the end of the alternating series test. It's not alternating in this case, but it's introducing, okay, well, alternating series introduce negative terms in a very methodical way. Here, what if we don't? And can we still answer it? Yes, we can get around it, thinking about absolute values of things. But the main idea here is alternating series, right? If I alternate series with that -1 to the n term or -1 to the n plus 1, it's kind of nice because then I only need to check two things. I need to make sure that the sequence goes to 0 and it's decreasing. If it doesn't meet those conditions, though, we don't have an answer, and we're going to wait till the next section to talk about what we call the ratio and root test, and that's going to talk about absolute convergence in general, taking absolute values of things, making everything positive, and then we don't have to worry about not meeting those conditions. And so that's going to go into the next test, but we'll leave it here in terms of the alternating series test, kind of nice little section with a nice type of series, alternating series. And so I'll have one more video in which I will do the proof of the alternating series, because of course, why is it so easy for an alternating series to converge? Why do I only need to make sure I satisfy these two conditions? Well, that requires some proof, some work. And that will be a separate video. It's not a required video to watch. It's just more of a justifying why this is such a nice and easy test. But other than that, we'll come back and we'll go into the next section, which is the ratio and root test.